I'll describe the Euclidean algorithm to find the GCD of two numbers. Two integers a and n. I'm assuming n is non-zero, and for simplicity I will assume n is greater than a. For simplicity we don't need to do that, so I'm going to do, to be able to write a computer program to help you with that, I'll just relabel these things. I'll let R0 be n and R1 be a. So what we're looking for is the GCD of R0 and R1, which is really the GCD of a and n. So I'm going to divide n by a, and I'm assuming that the quotient is q and the remainder is r. So if you divide n by a, r0 by r1, you get the first quotient with a remainder of r2. And I will assume r2 is greater than r1, r2 is less than r1, greater than 0. It should be less than r1, otherwise it won't be the remainder. And we'll continue dividing r1 by r2 to get the second quotient. And then the remainder are, let's call it r3. Okay, and divide r2 by r3, you get q3, and the remainder r4. And continue doing this until you get rm minus 2, which is qm minus 1 times rm minus 2 minus 1 plus rm. I will assume rm is positive, but then the next quotient I will assume is 0, I mean the remainder. So rm minus 1 will be qm rm plus 0. So in this case now, it's not hard to prove, it's very easy to prove that the GCD of R0 and R1 is actually the GCD of R1 and R2, which is really the GCD of Rm minus 1 and Rm minus 2. This is Rm. And now I'm going to do an example on this, and I will actually calculate the inverse of two numbers. So one thing we need to recall is that A inverse mod n exists exactly when the GCD of a and n is 1. Otherwise, A is not invertible mod n. So we'll see if I can calculate the GCD of two numbers and actually even compute the inverse. So then first calculate the GCD of 357 and 1, 2, 3, 4, and then we'll compute 357 inverse mod 1, 2, 3, 4.